All right, so I know we're competing against lunch here, but I'm not going to wait till all the stragglers get in. We're going to go ahead and get started. My name is Allison Klein. I'm the Senior Lead Program Manager for Direct3D Technologies, and I'm very excited today to be talking to you about the improvements we're making for Direct3D in Windows 7. Now, we're up against lunch. I know you guys are tired. You know, you've had all these people just shoving information down your throat. I also have a hard time, myself personally, just paying attention for a full hour at a time. So what I like to do is start my talks with what I think are the key takeaways. So that way, you know, you're sort of prepped, you know what you should be getting out of this. And the first one is that we'd really like for you to start thinking about Direct3D as being for more than just games. Now, traditionally, people have really thought about us as the high-end sort of gaming and graphics API, and that's cool. But now that 3D hardware is sort of becoming more prevalent within the ecosystem and end user expectations are getting higher and higher just about basic visual quality, it's really time to start thinking about using 3D graphics for more than just games. And to help you do that, with Direct3D 10, what we're presenting in Windows 7 is a complete end-to-end graphics platform that scales all the way from Direct3D 10 hardware down to a very performant software rasterization solution, so that you can really have a stable and predictable rendering environment for your 3D applications that you know can run in a variety of hardware scenarios. Now, we're also going to talk about Direct3D 11, and that is, of course, the next level in cutting-edge graphics. It's really important for people to understand that this is a strict superset of Direct3D 10 and 10.1. So unlike the big change that we made from Direct3D 9 to Direct3D 10, here we're just adding stuff to the API. Okay? However, the features we're adding are aimed at improved visual quality and improved performance, and we're going to talk about those today. And so you can kind of think of this as a sort of cascading model of Direct3D evolution, right? DirectX, Direct3D is the version for, you know, the widely available hardware that's, you know, out there in the ecosystem. And N+1 is sort of a preview of, hey, these are the new cutting edge features that we expect to eventually become widely available. So with those key takeaways in mind, here's how I'm going to get you there. We're going to start off with a scenario of a sort of heterogeneous environment and how Direct3D 10 can be deployed within that environment. And then we're going to move on to talking about high-end graphics for the second portion of the talk. And, you know, then we finish with summary and questions, like all these talks. So we're going to start with our friends Fabricam, right? So Fabricam is a company that designs and manufactures industrial widgets, right? Now, maybe they use somebody else's CAD/CAM software and they write their own 3D plugins, or maybe they just write their own software. We saw a very nice example of this actually 2 days ago in this very room when Anantha Kancherla had Dassault Systems come up, and they gave an example of a very nice design application they had written in Direct3D 10. So the key thing is that whether they're writing their own software to plug into somebody else's or just an entirely custom solution for themselves, they definitely rely on 3D graphics. But when they look at their users, they have a variety of users. So there's some people who have these great high-end desktops with Direct3D 10 hardware. Some of their users have laptops that still have Direct3D 10 hardware. So these are still, you know, they're really nice laptops, not maybe quite as beefy as the desktops, but still really good. But because, you know, this is either a large corporation or they have a very diverse user base, they also have some users who are still on Direct3D 9 hardware, right? You know, even if the IT department would like everybody to be running on the same hardware all at once, it can take a while to deploy that. Or again, maybe they work with external partners and they don't dictate the hardware at all. And finally, they might have some hardware that has no graphics support, graphics hardware support whatsoever. And this includes the headless server scenario. So the question is, how can Fabricam write a graphics application that works across all these configurations? And so that's what we're going to talk about. And we're going to start with, they should start architecting their application on Direct3D 10. Now, a totally, you know, common sense question to ask is like, well, why start with Direct3D 10? Like, why not start with something lower common denominator like Direct3D 9? Well, first of all, Direct3D 9 won't work on that server scenario, the headless server scenario that we talked about. But in addition, there's some other really good reasons to target Direct3D 10. it's going to give you a much more consistent experience across the hardware. So one of the things we did when creating Direct3D 10 was we wanted to really clean up the API, making it faster and easier to code to than Direct3D 9. We gave it a more efficient DDI so that there was more opportunity for significant driver optimizations. And we're really seeing this in the ecosystem today. The drivers are just continuing to improve and continuing to improve. We gave it a tighter specification. With Direct3D 9, there was a lot of undefined behavior. And what that meant, undefined behavior in the hardware spec, excuse me. And what that meant was that IHV number 1 could implement a feature one way, another IHV could implement it another way. They were both consistent with the spec because that behavior was undefined, but for you, the person writing the code, it gave you different rendering results, and that's no good. And finally, we eliminated caps. Now we're going to have a brief digression to talk about caps. Because this isn't an expert course, I assume most of you actually know about caps, but just in case, let's talk about them a little bit. So caps are the individual capabilities bits that each IHV added to their own Direct3D 9 hardware. Now Direct3D 9, of course, was a tremendously successful API. It was out there for a while. And so what IHVs started to do is they said, hey, we've got this really cool feature that we want to expose on our hardware, to help us differentiate. And so then they said, there are these little bits that people can check for, and that would expose, okay, fine. So one IHV would do that, another IHV would do that, so on and so forth. And we wound up with this. Now, I know you can't read it. This document actually is in the SDK, so if you've ever installed the DirectX SDK, you have a copy of this document. And the reason it's so small is that's the only way I could fit it onto the page. And you can see that this little yellow box there expands to that there. So you can get a feeling for how much information is actually buried in the rest of that document, right? So this is what we wound up with, this super complicated matrix of capabilities bits that graphics cards had. Okay, so it's huge. So of course, this made code writing way less than optimal, right? Because now you had to sort of do all these different code paths and be checking for these capabilities bits, because in some case it was really cool and you wanted to expose it, but if this other user didn't have that card, you just wound up with this super complicated code flow. So code writing was less than optimal because you had to do lots of checking for caps bits. So with Direct3D 10, we just drew a line in the sand and said, that's it, no caps. So with the elimination of caps, again, we're trying to get to that more consistent experience. Okay, so you really know how Direct3D 10 is going to look out there across the different kinds of hardware. So this is a diagram we're going to be looking at building on for the rest of the talk. So just to make it clear what we're talking about, we have an application. It talks to the Direct3D, in this case 10 runtime, because that's what we're talking about right now. That, of course, talks to a Direct3D 10 driver. We could have 10.1 in here, too. 10 or 10.1, 10 or 10.1 driver, and then the 10 or 10.1 hardware. Okay, so that's sort of the basic architecture of how these things work. All right, so we've figured out sort of, okay, use Direct3D 10 for these users. They have the hardware. It's a cleaner API. You're really going to know how things are going to look when it renders on that hardware because of this tighter specification and the elimination of caps. But that gets us back to how do we then make it work for these folks? And so to talk about that, we're going to introduce something called Direct3D 10 Level 9. Now, getting back to this diagram that I showed you just a few minutes ago, the important thing to understand about how 10 Level 9 fits in with this is that it's basically a driver that we provide that lets you talk, that lets the 10 runtime talk to 9 hardware. Okay? So that's all it is. But going back a few more slides, there was this whole thing with caps, right? And so all these cards had different capabilities. And so we wound up with this sort of ecosystem of all these different capabilities that the cards had, and it's represented by the starfish and the jellyfish and the sharks up here. So how are we somehow going to take all those different capabilities and yet make them work with this cleaner, sort of leaner API? And the idea is that we're going to bucketize these features into 3 big buckets called feature levels, and that's what you're going to target. So let's talk a little bit more about these feature levels. Feature level is basically a modification to the create device call that allows the D3D10 device to be created with flags that specify the desired feature level. So now, and you'll see a code sample of this in a minute, so if that doesn't make any sense to you, don't panic. So now the create device call has been modified to let you know what level of device you want to create. And if you try and create a device that has functionality greater than the card you actually have, the create device will fail. Okay? So it'll fail if any of the features in the specified feature level are not supported. So you can't somehow, unless you don't check for errors, but you can't mistakenly create the wrong level of device. Okay? So basically what we're doing here is we're going from hundreds of these caps bits, maybe thousands, I never actually checked, but lots and lots of caps bits, certainly, which is this very fine-grained control, to 3 levels, which is coarse but manageable control. And the 3 levels here are feature level 9_1. This is the lowest feature level. 9.2, which is slightly better, and 9.3, which has slightly more features. So looking at this again, these are the kinds of cards or graphics support that we have in feature level 9.1. And it supports shader model 2.0. So the point of this slide is just to give you a general feeling for the different feature levels. Feature level 9.2 is also shader model 2.0. It has some slight difference in features, and we'll talk a little bit more about that in the next slide. And there you can see some cards for feature level 9.2. And feature level 9.3 supports shader model 3.0. All this is going to be documented, so don't feel like you have to be scribbling this down. This isn't complete anyway. The important thing to realize, though, is that each feature level is a superset of the one below it. So feature level 9_2 has all the functionality of 9.1 plus some more stuff. Feature level 9.3 has all the functionality of 9.2 and 9.1 plus some more stuff. So this is an example of just some of the differences between 9.1 and 9.2. Like you can see max volume extent is slightly different, and these kinds of things. It's not a complete list. It's actually a fairly good one, but not a complete list. But again, the idea here is just to give you an idea about the differences between these feature levels. So now some of you are sitting there saying, you lied to me, right? You said you were getting rid of those caps. Isn't this just caps? Well, not really, because again, the idea is that the feature levels are much more simplified, right? And again, we're going from these hundreds of caps, this ultra fine-grained control, to much more coarse but manageable control with 3 levels. Okay, so hopefully you're sitting out there and you say, okay, this seems nice. We've got the benefits of 10 hardware, this coding to a simpler API, coding to a simpler, cleaner API where I kind of really know how things are going to look. It's on the 9 hardware, right? So I broadened my reach. But if you're like me, this kind of talk, I don't know, it's sort of hard for me to focus on, right? I like to look at code, and then I'm like, okay, now I understand how this works. So we're going to take a look at a code snippet very, very quickly. We have our device pointer here at the top, and here I've created an array with different feature levels. We're going from 10.1 all the way down to 9.1. So we're starting with the highest feature level and going on down. And now all I'm going to do here is when I'm going to go through this loop, as you can see. And when I create the device, I'm going to try to create the device going from the highest functionality to the lowest functionality. And remember again, I said create device fails if you try to create too functional a device or too high a device, right? So that's that level attempts level. That's where we're traversing that array that I showed on this slide here, going through the different feature levels. Okay? So that's it. That's now how you create one of these new devices with the feature level. So with that, we've got our users with 10 hardware, we've got our users with 9 hardware, and now what's left is the folks who don't have WDDM 1.0 capable hardware at all. And so that brings us to Direct3D Warp 10. Again, we have our application, we have the runtime. It's talking to the 10 hardware, it's talking to the 9 hardware, and now we're going to add one more thing in, which is the Direct3D Warp 10 software rasterizer. And that's all this is. It's just a fully software implemented rasterizer. And our criteria for warp development was really 2 things. It had to be 100% conformant with the Direct3D 10 spec. Again, we're getting back to, we want that predictable experience. We want you to know how stuff is going to run all across this platform. And performance, it's lots faster than RefRast. RefRast is designed purely for correctness, and it's actually also designed, the source code is designed to help our IHVs kind of understand our intent with some of these features, right? Now, in contrast, Warp, because we don't need to worry about, sort of making the code as human readable as possible or whatever, we can put all these optimizations in, we can write directly to assembly, we can do what we need to get it to be faster and faster. So the goal was to make it lots faster than Ref because it's aimed at a different target audience, and to make it fast enough for real-time use. So we're going to build on the slides that I just put up, these code slides. So this you've seen before. These were these different feature levels that we had for the create device, right? We're going to iterate through here. And of course, if we don't have a device there that any of these succeed with, we're never going to break out, right? We're going to run all the way to the end of this loop, and we won't have successfully created the device. And so then the last thing we do is we say, hey, if we didn't have success before, we're just going to create a D3D10 driver type software, okay? And this is, I believe this is the way the code looks if you try and run this with the M3 build. So that brings us to a very quick demo. Now, some of you saw this before if you saw Anantha's talk on Tuesday. This is one of the Direct3D10 sample apps, Bump Earth. And right now, we've got it running in hardware, right? You can see the frame rate there. Now I'm going to toggle it to Ref. And in this case, we're actually toggling it to Warp. Okay? So it's not the RefRast that originally shipped with the Direct3D10 SDK. And so you can see it's still got a very nice frame rate. It's certainly much slower than hardware, but it's still totally interactive. It's certainly good enough to feel like you're getting a good rendering experience there. And that's our goal. I mean, we certainly can't expect to be as great as software, but we still want this to be usable. Now, that's kind of cool, and we all like that kind of eye candy thing. But what I'm going to show now, whoops, this seems to have changed. Oh, that's fine. What I'm going to show now is just some office, sort of office type art rendering examples. And the reason I'm showing these is that because, this is the kind of stuff where if you're not doing games, this might actually be more along the lines of the kind of clip art kinds of stuff that you might be rendering. So I just wanted to put those up there. You can see the frame rates at the top. You can see that it looks really nice. It's rendering quickly. So the whole point there is that it's certainly good enough, we feel, to be, again, interactive, performant enough for you to use and feel confident about. It looks good and it's performant. So that's actually the end of the first part of the talk. If you have questions, of course, we can talk about those at the end. But that brings us now to moving on to Direct3D 11, which this is the high-end graphics scenarios. And we have a lot of content here. This is pretty cool stuff. So the scenario here that we're going to talk about is GamerCorp, right? So GamerCorp, they have complex shaders. They have really complicated environments. They have animation going on, lots of characters running around, all this stuff happening. And of course, they want this to happen at interactive frame rates, which is upwards of 60 frames a second. So what are the kinds of things GamerCorp actually cares about? Well, they're worried about scalability. So first of all, Anantha, again, in his talk on Tuesday, he showed this really amazing infographic, if you want to call it that, showing that even within Direct3D10 cards, there's just a massive performance difference between the low end and the high end. So even knowing that somebody has a D3D10 card doesn't sort of tell you that much necessarily about their performance. So you want to make it work well on those sort of lower end cards, and you want to make your game really shine on those higher end cards. Okay, so we want to be able to scale on that kind of hardware. Number of CPUs. There's certainly been a ton of talks about multi-core and many-core at this conference. We know that multi-core and multi-CPU is just becoming a way of life. Like even my laptop has 2 CPUs in it. So again, we want to make this scale so that it can really take advantage the more CPUs your end user has. And then display resolution. Another trend that everybody has noticed is lots of people have laptops with very small screens. Lots of people now, if you're like me and you have your gaming PC hooked up to an HD TV, like I've also got a super huge screen. So now as a game developer, what I have to worry about is I need to render it so it looks great on that HD TV, but at the same time, I don't want to render all that content if it's going down to a small laptop screen. Like, that's a lot of wasted effort. Nobody can see that. So we need to be thinking about scalability in response to display resolution. Performance is kind of, you can think of that as kind of being a form of scalability, right? Again, we want to make sure it performs well all across the spectrum of graphics cards and, again, across a number of CPUs. But performance is, it's so important to us. I wanted to call it out specifically. And the last thing is maybe not so much for this crowd, I'm not sure, but one of the things we definitely hear from game developers is, hey, you're Microsoft, and you guys do DirectX, and you do the Xbox, but it's not really this ideal experience developing for both of them if I want to develop a PC game and an Xbox game at the same time. So one of the big things we're working here to make much better is ease of cross-platform development. And in this case, cross-platform means between PC and Xbox 360. So here's all the stuff we're going to talk about with this new graphics pipeline. And we're going to start off with a new feature called tessellation. So this is a potential character authoring pipeline for a game. You might start off with your sub-D modeling, and then you're going to take that and animate it. And then you're going to add high-frequency detail with a displacement map. Now, you could actually do the displacement map before the animation, but you get the idea. This is just a general thing. The sad part is, now what you do is you take this and you dump it out to a polygon mesh. So you did all this modeling in one space, and now you're actually going to render it in a different space. And you might actually generate different levels of detail, but the idea is you've still got these sort of basically fixed polygon meshes to be dealing with. So we think about that pipeline in conjunction with some trends. And the first trend is that, of course, the characters are just getting more complicated, right? They're getting more detailed, denser, more triangles. Okay? So now we've got more triangles, and we add on to that the fact that we're actually putting more animation information on the vertices of those triangles. So not only do we have more vertices, but now we actually have more information attached to each of those vertices, right? Because we're expecting more complicated animations, better looking models, better looking characters. So the upshot of this is sort of two problems. The first one is that now that indirection of sort of doing all your modeling and animation in one space, but then actually rendering something that had a different domain becomes more painful, right? If there's any data loss in that conversion, okay, well, it only becomes magnified the more triangles, the more animation information you have. So that's kind of painful. The other thing, which is probably more visceral in a certain sense, is the I/O issues. So now we've just got much more data, which means it takes us longer to get that data from disk to main memory, and from main memory across a tiny little bus to the GPU. Okay? So this is really causing I/O, like significant I/O pain. So the solution is basically we want to be able to use these higher level surface representations longer, and that means adding tessellation to the Direct3D 11 hardware pipeline. So what we're doing is we're still taking this, but now we take all this information and basically send that to the GPU, and then we can tessellate that at runtime. And here, when I say optimally tessellate, it might mean a couple of different things depending on the scenario. So for example, we talked about laptops, right? Or if you're rendering the character to a small display or the character's far away, right? You don't need to create that many triangles. Okay? And with a fixed mesh, there's already a lower bound on the number of triangles, and you can't go beyond that. In this case, hey, you can go as low as you need to go. Conversely, if I'm on that great big HD TV, then great, give me more triangles. Or maybe I'm like zoomed in to the character, in which case I'm only seeing a little patch. Well then fine, just render that patch with lots and lots of triangles. But you don't need to worry about the other ones. Another way to think about it is if you find that performance is suffering, okay, I'm going to drop visual quality a little bit in order to keep my frame rate consistent. So you have all these sort of controls that you can have to make the decision. So what this means for the pipeline is we basically have the Direct3D pipeline. This is what we had for Direct3D 10. And we're just going to add 3 new stages for tessellation. There's the hull shader and the domain shader, and those are both programmable stages. And those are sort of sandwiching that fixed function tessellator. Now, unfortunately, I don't have time in this talk to explain what each of these stages does, and I'm very sorry about that, but we only have the time that we have. The important thing to understand is that while I am going to talk about features that will work on down-level hardware, on Direct3D 10 hardware, this is not one of them. It requires Direct3D 11 hardware. It's just too slow to do in software emulation. Okay? The other interesting thing to note is that the fundamental primitive here is a patch, because again, we're getting closer to the sub-D surface. And it's a superset of Xbox 360 tessellation. And what this means is that basically, again, we're really trying to make that cross-platform development experience better by, providing what you could already have on the Xbox 360. We have that functionality too, but at the same time, we're taking advantage of advancements that have been made in the PC hardware and graphics ecosystem since the release of the Xbox 360, and also building upon our knowledge and experience of what worked and maybe didn't work so well with the Xbox 360 tessellation. So we're still reproducing that functionality and building upon it. So here's some sample images. These come from the November SDK. All the stuff that I'm talking about is in the November DirectX SDK, and I'll talk about when that becomes available at the end of the talk. We have our fabulous clown model here. And so this is the first level of detail, the first tessellation level. This is level 2. Level 3, subdivision. This is actually now level 5. We skipped 4 just to make it more interesting, and all the way up to level 7. I just want to tell you a little funny story about this, which is the art guy who's the content manager. He came in when he's like, look, I've got the clown. And everybody on the dev team was like, I hate the clown. So the clown's actually going away for March SDK, but you're stuck with it for November. So the way I like to think about tessellation is it gets us closer to eliminating pointy heads, right? And this is the thing, if you're a gamer like me and you zoom in close to your character, God, it's so distracting. You start seeing like the creases in their head. More formally, what this is doing is it's scaling visual quality across PC hardware configurations. Again, we talked about, PC hardware configurations meaning different graphics cards, meaning different display resolutions. It also supports performance increases in 2 ways. First, this coarse model really is a form of compression, right? It means faster I/O from disk to main memory and across the bus to the GPU. And again, rendering can be tailored to each end user's hardware. We don't need to render stuff unnecessarily if the display is small. Or again, if we notice that frame rates are dropping, we can just make the choice to decrease visual quality in favor of consistent frame rates. It's also, again, getting back to that idea of cross-platform experience with Xbox, Windows and Xbox. And finally, I think the important thing is we're just getting closer to rendering the content as the artist created it, right? And that's really what people want, okay? They don't care when you're looking at somebody's, 3D, whether it's a game or something else, you don't sort of care the technology. You just want it to look good. And that's what the artist is all about, and we want to enable the artist to do that. Now we're going to talk about another feature, multi-threading. And multi-threading today, a very common scenario is you might have your physics simulation running on one thread, your AI simulation running on another thread, and the graphics portion of your app running on a third thread. And that, of course, is what's talking to the GPU. But there's a problem if it's the CPU-bound, if it's the CPU-bound portion of your app that's really holding things up, right? Basically, the little hamster on the CPU is running as fast and fast and fast as it can, and meanwhile, the GPU is just waiting idle for something to happen. And we're getting closer to Halloween. For us in the graphics team, that's a nightmare, right? That's like Nightmare on Elm Street. The GPU is waiting idle. So we want to do everything in our power to make sure that doesn't happen. And what we're doing is we're enabling multi-threading then, or improved multi-threading, I should say, on Direct3D 11. It was available on Direct3D 10, but we're improving it in 11. And basically what we're doing is we're enabling distribution of the application code, of the runtime, and of the driver across threads. We're also providing an immediate context. That's the thing that talks to the GPU, plus deferred context. And what the separation does is it enables an application to, say, load a texture or compile a shader on one thread in such a way as to not significantly impact the rendering portion of the app. In addition, we've made object object creation entry points, sorry, free-threaded. So you can have many threads creating objects simultaneously. And again, for those of you familiar with Xbox 360, this basically enables the same scenario as precompiled command buffers. Now again, in terms of key takeaways, one thing I really want people to understand is that Direct3D 11 multi-threading will work on Direct3D 10 hardware. And so we definitely see significant utility for this. We see a lot of people just right out of the gate basically doing Direct3D 10 plus the 11 multi-threading because there's no reason not to. It's going to work on the hardware that's out there. So the following now can be distributed across threads. That's the upshot of this. The application, of course, the 11 runtime, that doesn't change. The 11 drivers, and if your friendly neighborhood IHV chooses to provide an updated driver, that can also take advantage of the multi-threading on 10 and 10.1. But saying it this way is a little bit confusing. So let's go back to our architecture diagram. And so here I've shown the application and the Direct3D 11 runtime, because that's what we're talking about now. And they have this sort of nimbus, this glow around them that's supposed to represent multi-threading. I didn't know how else to do that. So they're multi-threaded. They're talking to the 11 drivers. These are the new drivers for the new hardware. Those are also cognizant of the multi-threading capabilities, so they're also distributing themselves across threads, and that talks to the 11 hardware. But it will work with your existing 10, 10.1 drivers and hardware. So that's super important to understand. However, if the IHV chooses, they can release an updated driver that will also be able to take advantage of this multi-threading. Okay, so it works great on the existing hardware and drivers, going to work even faster on the newer hardware and drivers. The whole point of this feature is to improve performance, of course, and we see it when we're thinking back about what does Gamer Corp care about, and they care about scalability and performance. This is scalable in two ways. The number of CPUs, of course, that's the whole point of the feature. And also, again, these graphics cards and drivers. It's going to work on the existing stuff today. It's going to work better and faster on the newer stuff. Let's see how we're... So dynamic shader linkage. Shader issues today. Sounds like a magazine or something. Thanks for your pity laugh down in front. I appreciate that. So shaders basically are getting bigger and more complex, right? Again, our expectations for how graphics look are just going up and up. They don't decrease, they only increase. So now we have, more complicated subsurface effects, more complicated material properties, more complicated lights, more material. I mean, all this stuff. It's just getting bigger and bigger. But again, shaders need to target this wide range of hardware, right? Even within Direct3D 10, there's a wide range of capabilities and performance. So what winds up happening is that developers wind up optimizing their shaders to take advantage of these different configurations. Right? They wind up just spending a lot of time just tuning these shaders to plan for all these contingencies. So one option that we see people do is the Uber shader, right? So it's basically this big, huge shader where they're using program flow control to basically see what, control what happens, right? So here we're saying, hey, maybe if I've got, this particular case, the graphics card's really awesome, whatever, do this super complicated material, okay, that's causing too much register pressure or something like that. So then I'm going to try the second material, it's not working so well, so on and so forth, until you finally, get to the material that's working for you. And you're going to do the same thing with a number of lights. Let's start off with 20 lights, like, not working so well, 19, so on and so forth, until you finally get to the lighting model that works for you. We also call this the one shader to rule them all model of coding. And there's some things that are, kind of good about this, I guess. All the functionality is in one place, kind of convenient. It reduces expensive state changes at runtime. That we definitely care about. One compile step, nice. And I don't know if this is really good or not, but we definitely notice a lot of people seem to do it. Okay, seems to be a popular coding method. What's bad is, of course, there's a reason that people like to write smaller functions that call other functions. This leads to very complex, unorganized shaders that are very hard to read. And probably more importantly is that register usage always winds up being worst case path through the code because the compiler doesn't know, right? The compiler says, hey, I don't know how you're going to execute through this code, so what I have to do is I have to allocate registers based on the biggest register hog in that whole code path. Okay? And register pressure is definitely something that affects performance, and so this is really bad. This is not what we want. Now, another option is to do multiple specialized shaders for each combination of settings. Okay? So this is good because then you're going to use the shader function that you actually need, and you're going to get the optimal register usage for that function. It's easier to think about, when you're writing the code, it's easier to think about optimizations, right? Because like you're saying, okay, I have exactly this number of lights and exactly this material. And for the compiler, obviously, it's much easier for the compiler then to tease out those optimizations. So in two ways, it makes it easier to target optimizations for this kind of code. What's bad is that there's a huge number of resulting shaders, because now you've got this like n by m matrix of shaders that you need to write. So it's, this huge explosion in the number of shaders you have to do. It's still a lot, I think, to think about, and it's just a pain to manage at runtime. Okay, there's definitely state change costs there. So what we've done is try and take the best of both worlds and introduce new constructs into the HLSL programming language that can be used to sort of get the best of both worlds. We want to get that better register usage while at the same time making code writing easier and cleaner. So in the runtime, what you're going to do is select the specific class instances you want. The runtime is going to inline those methods. Okay, so that's what gets you the good shader or good register usage. The inlining is done in native assembly, so it's nice and fast. And this applies to all subsequent draw calls, so you're less worried about state changes. So this is sort of the difference between the Uber shader code and the new dynamic subroutine code. And here what you're doing is you're binding the appropriate one at runtime. Okay, on to improved texture compression. So why do we need new texture formats in Direct3D 11? Well, a couple reasons. One, the texture compression that we use in Direct3D is what's called block compressed. Again, I think probably a lot of you know that already, but in case you don't, they're block compressed. So you take each block of the texture, you're going to compress it individually. And the interpolation models that we have for the existing BC formats, as they're called, are too simple. And so the problem is that the results, and you're going to see this in a couple of seconds, the results often have significant blocking artifacts. Okay, so that's really unattractive. We've all seen this. We also don't currently have high dynamic range support. And people really want this for bloom effects and other sort of complex lighting effects. These definitely are issues that we heard directly from developers, like, hey, fix this. We don't like it. It doesn't look good enough. So because of that, we have two new block compressed, or BCs, for Direct3D 11. The first one is called BC6. Sometimes it's also referred to as BC6H because it's the HDR compressed format, or high dynamic range, I should say, format. It offers fixed compression, 6:1 compression, going from 16 bits per channel. And it's targeting high but not lossless visual quality. None of the BCs are lossless. BC7 is the new improved standard dynamic range rendering format. It also supports alpha, so you're going to get 3:1 compression for RGB or 4:1 for RGBA, and this is targeting improved visual quality. So what stays unchanged, just to make it a little bit clearer, is each block is still compressed independently. That's what we want, because that's how the hardware can, just grab the pieces it needs and decompress those quickly and easily. And each block still has a fixed compression ratio. That doesn't change. But what does change is now the compression is tailored to the individual block content, right? So you can imagine that if you have one block that has a smooth color gradient, it's just going from white to pink, you can compress that in such a way as to get lots of fidelity along that gradient, really get that nice smooth gradient. Versus if you have a sort of very noisy image, right? Well, you don't need as much fidelity for each individual color, right? But you want to be able to represent that full space. And so the kind of interpolation you're going to use for those two different things is going to be very different. We also represent, I should say that compression, this new compression scheme, takes into account varied alpha versus constant alpha. So basically, we're just doing a better job of compressing different types of content because we're adding more complexity into that compression and decompression. Another big difference, and again, this gets back to this philosophy of we really want consistency, is the decompression results must be bit accurate with the spec. So this is something new, and people are very, very happy about this. So let's take a look at some example images now. So we have the original image here on the left, and we have the decompressed results using BC3, which is a fairly popular existing BC, and BC7. And what you should be able to see, and the projector's pretty good, I think you should be able to see it here, is that there's significantly more blocking artifacts with the BC3 image than there is in the BC7. And even if you can't see it in the decompressed image, you can definitely see it in the absolute error image, right? The BC7 just has a lower absolute error, so that's what's in the center. This is another example. These are normal maps. Again, the BC3 image, it just looks chunkier and blockier, and you can certainly see that in the absolute error image in the center. One last comparison, this is the HDR content displayed at a given exposure. So again, we have the original on the left and the decompressed BC6 at the right. There's nothing older for us to compare it to, so that's why you only get one comparison image. And here, what you should notice is when we look at the absolute error image in the center, it's just got this diffuse noise pattern. And that's exactly what we want. That's a good sign, because the human visual system has evolved to really notice blocks and lines and edges, okay? So when the error comes out as this kind of diffuse noise, it's much harder for us to see. And so again, this is what we want. This is good. Looks nice. All right. Now we're at the portion of the talk that I bet most of you are actually the most excited about. We're going to talk about the compute shader. So to do this, we're going to talk about a slightly different scenario. Now I'm going to talk about VisCorp, right? VisCorp is not GamerCorp. Maybe what VisCorp does is they have high-end visualization software. They might do a lot of image processing type stuff. In this case, what I'm showing you is they have an image that has a very significant houndstooth dithering artifact in the area outside of the yellow box. Okay, so again, in the area outside of the yellow box, you can see this dithering artifact. Now, a way to get rid of this is you basically take an image and you put it in the frequency domain. Okay, so we've done an FFT, fast Fourier transform, on this image. We put it in the frequency domain. And from there, what you can do is sort of look for specific patterns in that frequency domain and remove those areas of energy. So those are the areas that have been sort of edited within the Ren circles. They had these high white areas of energy, and they've removed it. And so that leads us to what's inside the yellow box, and you should be able to see that it has much less of that houndstooth dithering artifact. From here, I can't see if it's really showing up, but it's there. So these kinds of things are what lead people to look at the GPU for improved data parallel computation, right? So again, if you've attended any of the other parallel computation courses here at PDC, you know, everybody's saying, look, the CPUs aren't getting faster. We can't rely on that anymore for improved performance. But the GPU performance continues to grow. And when we think about that in conjunction with the fact that there are lots of applications that are very easily sort of mentally to wrap your head around the parallelization of it and then to code up, right? So again, thinking about just image processing, if you have something like for each pixel I, do the same thing, right? I mean, that's a super, like, that's, you know, that's sort of the easiest parallel thing you can think of, right? So there are lots of applications that scale well to these sort of very large parallelism changes, but without requiring tricky code changes. And since Direct3D is the API for talking to the GPU, it makes sense for us to think of, okay, well, how can we expand Direct3D to be more sort of, to expand the kinds of computations that we could do. Now, the stuff I'm going to talk about here, you could actually do before. It was just tougher. We basically, you could still sort of get at a lot of this parallelism that I'm going to talk about here, but you just had to like put a, you know, draw a triangle at the end. And so it wasn't sort of as natural as it could be. So again, we're just extending the HLSL language. We're building on what we already had to add this in. So this more general purpose parallel computation stuff, we're calling this the compute shader. Okay? It fully supports all Direct3D resources. We're targeting especially graphics and media data types to begin with. But it is, again, a direct evolution of HLSL, right? We're just adding stuff onto this parallel programming language that lots of people already know. So basically, the graphics pipeline has been updated to emit general data structures that can then be manipulated by this compute shader and then rendered if you wanted to by Direct3D again. This isn't the only way you have to use it, but it's an easy way to think about it. And so that's how we're going to talk about it for the rest of this talk. So getting back to our pipeline diagram, what we're doing here is we're going to say render a scene. Then we could write out that scene image, right? So we're going to write it out to some data structure. Then we're going to put that over in the compute shader, and maybe we're going to use that for image post-processing, right? And then if you wanted to, you could output the final image. This is an example scenario. Note that the compute shader is not a stage that runs sequentially within the pipeline. It's its own thing. So some of the features that it has, again, there's much more documentation on this, but some of the features that it has are 1D, 2D, 3D thread invocation and arrays. Again, like I said, you're no longer forced to draw a quad anymore to get the actual thing you wanted at the end. Shared registers, again, super important. You can imagine we're actually going to look in a few minutes at an example of, say, you might calculate the average intensity over an image, and then you might want to, for each pixel, move it either closer to or farther away from that average intensity, depending on the operation that you're doing. Well, the average intensity isn't changing over the image, right? So we want to store that in one register that then all these threads can access, right? Because, I mean, we don't need to spew that everywhere. It's the same value. So this obviously reduces or can eliminate redundant computations. You can also read and write to arbitrary data structures. And the idea here is that, yeah, we really want to enable these new classes of algorithms on the GPU, but it's still integrated with Direct3D resources. So initially, the kinds of applications that we see people sort of doing the first uptake on are image post-processing. So I'm going to show you an image reduction example in just a second, but histograms, convolutions, FFTs like we've seen to eliminate artifacts, a whole bunch of stuff. That's kind of the low-hanging fruit, if you want to think of it that way. People are also talking about A buffers or other forms of order-independent transparency that we can get. Then we move on to ray tracing, which people are always talking about, ray tracing radiosity. And ultimately we could do physics, so fluid flow simulations, other grid-based computations are sort of very natural things to make parallel, and AI simulations. So again, initially we're targeting sort of image post-processing, but I want to make it very clear. This is a long-term direction and investment for us, right? So this is the first step, and we intend to keep building on this functionality. So as I mentioned before, I like to think, see things in code. It kind of makes it more concrete, more tangible for me. So we're going to go through an example of image reduction. So what we're going to do here is we're going to find the average intensity of an image. You might use this for high dynamic range exposure adjustment or other things. When we think about this, we might have a 1K by 1K image, so that winds up being 1 million pixels, right? And we basically have one multiply add per pixel, right? So I'm going to take the pixel, I'm going to calculate its luminance, right? I'm going to divide that by the number of pixels. So 1 over the number of pixels, that's the multiply. We add that to our final result. So that's how we get that multiply add. And the output is one value. So it's this 1,000,000 to 1 reduction. And if you want to think of it this way, it's this huge input to dink, this tiny little output. So let's start with just thinking, we'll think about this algorithm in the simplest way. And this is the not parallel version of this. So don't anybody run back to your blog and post it and say, this is what compute shader code looks like. This is the not parallel version of it. Somebody's going to do it, though. I'm right. So basically, this is what I just talked about, right? For all pixels, get their intensity, and then divide that at the end by the number of pixels, and that's the average luminance. So that's just to make sure we're all talking about the same problem. So here's the first example of this reduction compute code, right? So we're going to have a group shared int, which is the total we have so far. Another group shared int, which is the count, how many pixels we have, okay? And then we're basically going to, using different threads, we're going to load that up, calculate the luminance, basically cast it to a uint there. Then we do this interlocked add, okay? So here we're doing memory protection there, right? We're going to add that to the count. Well, we're going to increment the count by 1, right? We've processed another thread. We're going to do the interlocked add to the total, saying, hey, here's the most recent luminance I got. Let's add that to the total. Synchronized thread group that says, hey, let's wait until everybody's finished. I've just repeated that on the top of the next slide, so we just have some continuous flow control. So let's repeat that. We're just going to wait till everybody finishes, and then at the end, we only need the first thread to go and say, hey, give me the average. So that's okay. It's parallel. We can do better. How can we do better? Well, basically, what I've done with this code is I said, hey, everybody go off and do everything in parallel and then go stand in one line. It's like what they make us do at lunch here, right? There's all these tables. Please go stand in that first table, right? And you're looking at all the other tables like, I want to eat. So these guys want to eat, basically. We can do much better. So let's look at another code example of how to do better. So here, what we're going to do is break this across 32. We're going to create 32 lunch lines, as it were. So now we have 32 of these totals. We have an array of that, 32 of these counts. We're going to do the same thing that we did before, but now instead of making everybody wait in one line, with those interlocked adds, they get to wait in 32 lines. Okay. Everything's the same. Then at the end, that first thread's just going to go across and do that last sort of summing up. So this sort of, pyramidization, this is a pretty common construct in parallel programming. I'm sure you've all seen it before, and this seems really trivial. And of course, there's a trade-off between how many of these lunch lines do you create, based on your memory and things like that. But it gets the idea across. So this is obviously a super trivial example of the kinds of things we're enabling with compute. The compute stuff is documented in the November SDK. You can do much more interesting stuff. Just in the context of this talk, I just wanted to make it concrete about, we're basically enabling the constructs you know and love in parallel programming. So again, protected reads and writes. There's different levels of locking that you can do. Of course, the tighter the lock, the more of a performance trade-off that is. There's nothing new. So you can sort of read about all those things. The idea, getting back to the summary, is this enables much more general algorithms to be moved to the GPU to take advantage of the increases in GPU performance. It's this transparent parallel processing model. It does have full cross-vendor support. We've been working with all the IHVs to develop this compute shader. So they're all in support of it. They all helped us design it. We didn't design it in a vacuum. This is also exciting. It's going to run on DirectX 10 and 10.1 hardware using shader model 4.0 parts. With these features, this will require an updated driver. So with the multi-threading before, remember I said, hey, it's going to work just as is. This one actually, it'll work on your 10 hardware, but you have to get an updated driver for that. And again, on the newer hardware, with the newer shader model, you'll have even more functionality. But we're trying to make it, give it the broadest reach possible. And so again, we're targeting older hardware and newer hardware. How are we doing for? I talked too fast. Okay, so we're at the end now. Sorry, we're at the end now. There's just a plethora of other features that we've put into Direct3D 11 that we're not going to talk about today. Some of them are, so addressable stream out. That means we already had stream out functionality, but we've increased the stream output buffers to 4. And you can change all the stream output buffers to be multi-element if you want. Coverage is now a pixel shader input. What else do we have going on here? Pull model for attribute evaluation. That's the ability to evaluate attributes within a pixel, somewhere on a sort of predefined multi-sample grid. Let's see. There's improved Gather 4 support. We now support multi-component textures with Gather 4. There's now required 8 bits of subtextual and sub-MIP filtering precision. So again, we've tightened the spec up there. Optional double support, increased resources, things like that. So a whole bunch of new functionality coming online. So for Direct3D 11, the summary here is that, again, I want everybody to understand it's just a superset of 10 and 10.1. It adds support for features like multi-threading, like tessellation, like the compute shader. You know, the fastest way to move to 11 is actually to start becoming familiar with 10 and 10.1 if you're not already. This will be available on Windows Vista and Windows 7. It'll also run, as I mentioned before, on down-level hardware. So multi-threading and compute, 10 and 10.1. You can also get to 9 via that 10 level 9 that I talked about earlier. Probably not going to give you screaming performance, but depending on the scenario, it might be useful. Full functionality for some features, like tessellation, that will require 11 hardware. So when can I get it? So the bits, of course, the DLLs, the system DLLs, are already on that snazzy hard drive that you guys got. In terms of the SDK, it's going to come out in the November SDK. That should be posted within about a week. Okay? The SDK will work on Vista and Windows 7. It will work on 10 hardware. You also have Ref, which, as we know, that's slow, but it's there. And it's going to have documentation and samples and, you know, sort of everything you expect from the SDK. This is the initial version, so we do expect to get more samples in there, you know, as we're going on. This is the beta version, so everything will be getting better. And as I mentioned before, check with your friendly neighborhood IHV for updated Direct3D 10 and 10.1 drivers. I don't have anything I can announce here today, but you might just keep your ears open for that kind of information. So that actually leads us to the end of the talk. So again, in terms of key takeaways, Direct3D, it's not just for games. What we've tried to do to support that message is provide you with this complete end-to-end rendering platform, right? That's going to give you a stable development environment, stable rendering environment with predictable rendering results across this breadth of hardware, from 10 hardware all the way down to software rasterization. There's also Direct3D 11, and that's sort of the newer cutting-edge features. Again, this is part of that sort of cascading model of Direct3D evolution, right? So for the features that have, you know, we see this as the features that have widespread hardware sort of adoption out there in the ecosystem. That's the platform for these sort of more line of business kind of applications, those sorts of things. And for that really cutting edge stuff, the games, those kinds of entertainment applications, or high-end scientific visualization, or high-end line of business applications, that's where Direct3D 11 fits in. I've also been asked to remind you to fill out your speaker evaluation for this session. And not just for this session, for all the sessions. We really do take this feedback very, very seriously. So even if you forgot to fill it out for another session, please go ahead and do so. If you liked the talk, certainly say that. If you didn't like the talk, now is a good time for quiet, personal reflection. You don't need to go, no. I mean, actually, even if you didn't like the talk, please, please, please fill that stuff out. It may not be apparent to you, I don't know, but Microsoft employees take this conference very, very seriously, and we do really want to do a good job for you. So if there's something that you see that you didn't like, please let us know, because I promise. And also, everybody's really competitive. People are like comparing their scores, so that's another reason that they're taking it seriously. So at that point, I'll turn this over to Q&A. Please use the microphones for people who are going to be watching this on video.
Hi, could you say what OS versions 10 level 9 and Warp 10 will be supported on?
Those are also supported on, they'll be supported on Vista and Windows 7.
Okay. And do you have any data about how many users have Direct3D 10 hardware versus Direct3D 9 versus, you know, no WDDM support?
I don't have that data off the top of my head. The 10 hardware is actually selling very, very well. So, so the 10 hardware is a logo requirement, so certainly everything shipping now with Vista has to come with 10 hardware. So it's really, to be honest, in terms of install base and the stuff that's out there, we see this more as a security blanket, if you want to think about it that way, that the 10 hardware really has widespread adoption, but there's still that those chunks, and like I said, it takes IT departments a while to roll stuff out. So it's kind of a security blanket, if you want to think of it that way. We certainly hear from lots of customers, like, I can't guarantee that 100% of people have this 10 hardware.
Okay, thank you.
Sure.
Hi. Do you have a plan for the fixed function?
For fixed function?
Yeah.
Well,
D3D10 is only the full shader.
I'm sorry, this is
Shader only.
only shader only?
Yeah. Correct?
No, I'm sorry, I'm still not understanding. So it's programmable. So you're saying there's no fixed function code, and I don't understand what you're saying. Oh, so you don't want to write shaders? Is that what you're saying? That you don't want to write shaders, and so you want?
No. Fixed function will be is available for D3D10.
Yes, parts of the pipeline are fixed function. And so certainly the functionality that you're used to, just the basic rendering functionality, that's certainly part of it.
Okay. One more question. Do you have a plan for the managed code?
So we do, but I have to be in that position of saying, but I can't tell you about it here. But keep your ears open. We definitely heard lots and lots of feedback about people were unhappy with our decisions about the managed code wrappers for Direct3D10, and I expect that you'll hear an announcement about that soon.
Thank you.
Sure.
Do you know if DWM will be targeting DirectX 10 in Win 7?
So Windows 7, yeah, it's written on DirectX 10. I think it's saying everywhere that it's 10.1. I think I've seen some news announcements, but it's 10. It's the 10 API, sorry. Again, 10 level 9, it works on 10 level 9 and all that stuff.
The software rasterizer, the Warp 10, will that support the new DirectX 11 features like tessellation and stuff like that? Is that
No, at this point it's Direct3D 10 only, but we expect to be evolving it. So I don't have anything specific I can say, or there's no nailed down plans for that. But
okay.
All right, well, I'll be standing here up front for a while if people want to ask questions then. Thank you very much.